Welcome to the world of real-time predictive control in robotics. In this video, we'll explore MuJoCo MPC, or MJPC, an open-source interactive application and software framework designed for real-time predictive control. Built on the powerful MuJoCo physics engine, MJPC makes it easier than ever for researchers and developers to author and solve complex robotics tasks. With its intuitive interface and robust set of planners, including ILQG, gradient descent, and the simple yet effective predictive sampling, MJPC aims to lower the barriers to entry for model-based control. Let's dive into how this tool is democratizing access to advanced robotics research and why it's making waves in the field. Predictive control has long been a cornerstone of robotics and automation. The core idea is to use models of system dynamics to optimize actions in real time, minimizing future costs or maximizing returns. Unlike traditional methods that require extensive computation or data, predictive control leverages mathematical models to synthesize behaviors on the fly. This approach is especially valuable in robotics, where quick adaptation and real-time feedback are crucial. MJPC brings these capabilities to your fingertips, making advanced control strategies accessible and interactive for everyone. Despite its power, model-based optimization has traditionally been difficult to implement. It often relies on elaborate algorithms and can be inaccessible to many researchers due to its complexity. MJPC addresses this by providing performant algorithms, simple code, and an intuitive, interactive software environment. Now, anyone can experiment with predictive control, tweak parameters, and see results in real time. No need for hours of waiting or deep expertise in optimization theory. Robotics, there's an ongoing debate between model-based and learning-based approaches. Model-based methods like those in MJPC use explicit models of the system to plan actions, offering speed and interpretability. Learning-based methods, on the other hand, let representations emerge from data, providing flexibility but often requiring vast amounts of data and computation. MJPC's approach shows that these methods can be complementary, and combining them could lead to breakthroughs similar to those seen in AlphaGo. One of MJPC's key innovations is its ability to provide instantaneous feedback. When you tweak a parameter, you see the effect immediately. This real-time interaction not only accelerates research but also enhances cognitive performance, allowing researchers to iterate quickly and gain deeper insights into their systems. The interactive simulation can even be slowed down, letting planners run faster than real-time, which is especially helpful on older or slower machines. MJPC is all about making predictive control accessible. By providing a flexible, interactive simulation environment with a researcher-authored graphical user interface, MJPC ensures that advanced robotics research is within reach for more people. This democratization of tooling is not just a convenience, it's a necessity for the next wave of robotics breakthroughs. Let's take a step back and look at the fundamentals. Optimal control is about choosing actions that minimize future costs or maximize returns. The system state evolves according to its dynamics, and the behavior is encoded through a running cost function. In MJPC, these concepts are implemented in a way that's both powerful and easy to use, allowing users to focus on designing behaviors rather than wrestling with complex math. Trajectory optimization is the process of finding the best sequence of actions over a fixed time horizon. In MJPC, this is handled through planning algorithms that can work with both direct and shooting methods. Direct methods treat both states and controls as decision variables, while shooting methods focus on controls and use forward simulation. Each approach has its strengths, and MJPC supports both, giving users flexibility in how they tackle their tasks. Predictive control takes trajectory optimization a step further by applying it in real time as the system evolves. The planner continuously measures the current state, optimizes the objective, and updates the plan. This approach is robust and adaptable, making it ideal for dynamic environments where conditions can change rapidly. Predictive control offers several advantages. Faster computation leads to better performance as more optimization steps can be taken in a given time. Warm starting, reusing previous plans makes the process more efficient. And because the optimization doesn't need to fully converge, researchers can get useful results quickly, even for complex tasks with long behavior timescales. One of MJPC's standout features is its support for derivative-free optimization, also known as sampling-based optimization. These methods don't require gradient information, making them ideal for tasks with non-smooth or discontinuous dynamics. They're also highly parallelizable, allowing MJPC to leverage modern multi-core CPUs for faster, more efficient planning. Sampling-based optimization methods maintain a search distribution over policy parameters and evaluate the objective at sample points. Popular algorithms include random search, genetic algorithms, and evolutionary strategies. While these methods are sometimes considered sample inefficient, in the context of predictive control, they can be surprisingly competitive due to their speed and simplicity. JPC is built on the MuJoCo physics engine, which is renowned for its speed and accuracy in simulating complex, high-dimensional systems. MuJoCo's ThreadSafe API allows for parallel simulation of multiple candidate trajectories, maximizing the use of modern hardware. This makes MJPC a powerful tool for both research and practical robotics applications. MJPC makes it easy to design and compose cost functions which define the objectives for your control tasks. With convenient utilities for specifying weights, norms, and residuals, users can quickly set up tasks that reflect their research goals. The system also supports risk-sensitive costs, allowing for nuanced control over behavior under uncertainty. Risk sensitivity is an important aspect of control, especially in uncertain environments. MJPC incorporates a risk-aware exponential transformation of the cost function, allowing users to specify whether the controller should be risk-neutral, risk-averse, or risk-seeking. This flexibility enables more robust and adaptable behaviors in a wide range of scenarios. JPC leverages MuJoCo's utilities for efficiently computing finite difference Jacobians and cost derivatives. By avoiding unnecessary recomputation and scaling well with input dimensions, MJPC ensures that even complex tasks can be optimized quickly and accurately. This efficiency is crucial for real-time applications where every millisecond counts. Reduce the search space and smooth control trajectories. MJPC uses spline-based representations for actions. Users can choose from cubic Hermite splines, piecewise linear interpolation, or zero-order hold. This approach not only simplifies optimization but also ensures that control actions remain within physical bounds, making it ideal for real-world robotics. JPC includes three main planners: ILQG, gradient descent, and predictive sampling. ILQG uses second-order derivatives for precise control, gradient descent leverages first-order information for efficiency, and predictive sampling offers a simple derivative-free baseline. Each planner has its strengths, and users can switch between them to find the best fit for their task. Predictive sampling is a straightforward zero-order method that iteratively improves a nominal action sequence using random search. At each step, multiple candidate splines are evaluated, and the best one is chosen as the new nominal. Despite its simplicity, predictive sampling can be surprisingly competitive, especially in real-time settings where speed matters more than perfect convergence. MJPC GUI is designed for intuitive interactive experimentation. Users can select models, adjust risk values, set cost weights, and modify planner settings all in real time. Live plots and simulation readings provide immediate feedback, making it easy to debug, understand, and refine control policies. This hands-on approach accelerates learning and innovation. Let's look at some real-world examples. In the humanoid standing task, a 27 degree of freedom system is tasked with standing up from the floor. MJPC enables the system to quickly stand and recover from large disturbances, demonstrating robust and adaptive behavior. Even if the humanoid is knocked down, it can stand back up, showcasing the power of real-time predictive control. The quadruped example, a Unitree A1 robot traverses uneven terrain, including steep slopes. MJPC's planners can adapt to slow machines by slowing down the simulation, giving the planner more time to compute successful strategies. The quadruped can even roll off its back and stand up, and can continuously navigate a series of target poses, highlighting the flexibility and robustness of the system. Hand manipulation task features a shadow hand performing in-hand manipulation of a cube to a desired orientation. This high degree of freedom system involves complex contact dynamics and is considered extremely challenging. MJPC allows researchers to set the target orientation in real time and observe the hand's adaptive strategies, solving a problem that was previously unsolved in real time from scratch. Key strength of MJPC is its robustness. Whether it's a humanoid recovering from a fall or a quadruped navigating rough terrain, MJPC's planners adapt quickly to disturbances and model mismatches. This adaptability is crucial for real-world robotics where unexpected events are the norm rather than the exception. Predictive sampling's effectiveness comes from its speed and simplicity. In real-time control, it's often more important to replan quickly than to fully converge on an outdated problem. The optimization landscape is constantly shifting, so staying in the basin of attraction of the minimum is more valuable than finding the exact minimum. This makes simple, fast algorithms like predictive sampling highly competitive in practice. MJPC is a powerful tool for task design. Researchers can quickly add new tasks, expose parameters to the GUI, and generate the desired behaviors. Once a task is designed and tested in MJPC, it can be re-implemented in other frameworks, making MJPC a valuable prototyping environment for robotics research. Another important use case for MJPC is data generation. By acting as an expert policy, MJPC can generate high-quality data for learning-based approaches. This data can be used to train reinforcement learning agents or to benchmark new algorithms, even if the model and task don't exactly match the learner's environment. For researchers focused on predictive control itself, MJPC is an ideal playground. Its asynchronous design allows for fair comparisons between planners, and users can switch planners on the fly. This flexibility makes it easy to experiment, benchmark, and innovate in the field of predictive control. MJPC's main limitation is that it can only control what MuJoCo can simulate, and only as fast as the simulation can run. Very high degree of freedom systems like fluids or soft bodies are challenging to simulate in real time. Advances in simulation technology or learned dynamics models may help overcome these boundaries in the future. Predictive control is inherently myopic. It can't see past its fixed planning horizon. This limitation can be addressed by integrating learned policies, value functions, or hierarchical control structures. For example, terminating rollouts with a learned value function can extend the effective planning horizon, while a high-level agent can guide the predictive controller toward long-term goals. By combining learned policies and value functions with model-based search, MJPC can achieve performance similar to AlphaGo's approach in discrete domains. This hybrid strategy leverages the strengths of both model-based and learning-based methods, opening new possibilities for advanced robotics control. While MJPC is primarily aimed at simulation, it can also be used to control real hardware. By generating data for transfer learning or coupling MJPC to real-time state estimators, researchers can bridge the gap between simulation and physical robots. This opens the door to practical applications in robotics labs and beyond. High-quality state estimation is crucial for controlling hardware, especially in dynamic tasks like locomotion and manipulation. MJPC's interactive GUI-driven approach could inspire similar interfaces for state estimation, making it easier to develop robust, contact-aware estimators for real-world robots. MJPC supports a variety of task objectives, from humanoid standing and quadruped locomotion to in-hand manipulation. Each task is defined by a set of cost terms, such as position, orientation, velocity, and control effort. This modular approach makes it easy to design, test, and refine new tasks for research or application. MJPC's planners can be tuned for different tasks by adjusting parameters like the number of rollouts, planning horizon, and noise scale. These settings affect both performance and computational requirements, allowing users to balance speed and accuracy based on their needs and hardware capabilities. MJPC is designed to make the most of available compute resources. By leveraging multi-core CPUs and efficient simulation techniques, it can handle high-dimensional tasks on standard hardware. This efficiency ensures that advanced robotics research is accessible to a wider audience, not just those with specialized equipment. MJPC is open source and designed to be extended by the community. Researchers and developers are encouraged to contribute, improve, and adapt the tool for their own needs. This collaborative approach ensures that MJPC will continue to evolve and support cutting-edge robotics research. MJPC stands out in the research landscape by offering a practical, interactive, and accessible platform for predictive control. Its combination of robust simulation, flexible planners, and real-time feedback makes it a valuable asset for both academic and industrial robotics research. Looking ahead, MJPC could be extended to support more complex systems, improved simulation techniques, and tighter integration with learning-based methods. As the field of robotics advances, tools like MJPC will play a crucial role in bridging the gap between theory and practice. In summary, MJPC is transforming how researchers approach predictive control in robotics. By making advanced algorithms accessible, interactive, and efficient, it empowers a new generation of innovators to tackle complex challenges and push the boundaries of what robots can do. Ready to try MJPC for yourself? The software is available open source, and you can find detailed documentation and example tasks online. Whether you're a seasoned researcher or just starting out, MJPC provides the tools you need to experiment, learn, and innovate in the field of robotics. MJPC thrives on community collaboration. Join the growing group of researchers and developers who are contributing to its development. Share your experiences, suggest improvements, and help shape the future of predictive control in robotics. MJPC isn't just for research, it's also a fantastic educational tool. Its intuitive interface and real-time feedback make it ideal for teaching concepts in control theory, robotics, and optimization. Students can experiment with planners, tweak parameters, and see the results instantly, deepening their understanding of complex systems. By lowering the barriers to advanced robotics research, MJPC is helping to accelerate innovation across the field. Its open, interactive, and efficient design is inspiring new approaches to both research and education, ensuring that the next generation of robots will be smarter, more adaptable, and more capable than ever before. Thank you for joining us on this journey through MJPC and predictive sampling with MuJoCo. We've seen how accessible interactive tools can transform robotics research and education. Whether you're designing new tasks, generating data, or exploring the frontiers of control theory, MJPC is here to support your work. Explore the software, join the community, and be part of the future of robotics.